Prime factorizations. This is a hugely important topic. First of all, here are the first 17 prime numbers, all the primes from 2 up to just below 60. And of course, the first 8, those are non-negotiable. You absolutely need to know those, and the others are very good ones to know as well. In the last video, I suggested that prime numbers were the building blocks of all the positive integers. Now we can discuss what this means. And in order to talk about this, I'm going to introduce the name of an important mathematical theorem, the fundamental theorem of arithmetic. I'll say right now, you don't need to know this particular theorem. As it was first discussed by Mr. Euclid. You don't need to know that, but you do need to know the idea of this theorem. Every positive integer greater than 1 must either A, be a prime number, or B, be expressed as a unique product of prime numbers. So in other words, every integer greater than 1 that's not prime can be expressed as a product of primes. And this product is called the prime factorization of the number. So that core idea you definitely need to know. Let's talk about this prime factorization. Let's do some examples. So first of all, 9 is obviously 3 times 3. It's a product of 2 prime numbers. 10 is 2 times 5. That's a product of 2 prime numbers. 12, we could write that as 4 times 3, but 4 isn't a prime number. 4 itself we can write as 2 times 2. So we can write 12 as 2 times 2 times 3. That's a product of prime numbers. 15 is 3 times 5. 24, we could write that as 8 times 3. Well, 8 is not a prime number. We can write the 8 as 2 times 4. 4 is not a prime number. We can write that as 2 times 2. If we had realized that 8 is 2 cubed, we could have skipped directly ahead to say that 8 is 2 times 2 times 2. Well, 2 times 2 times 2 times 3 is the prime factorization of 24. And in fact, we can even write this way with an exponent, 2 to the third times 3. Either way is correct to write it. When the numbers tend to get larger and you have lots and lots of prime factors, it's usually more convenient to write it in exponent form simply because it's more compact. So here are some larger numbers. Now 100, you might be able to see 100 is 10 times 10. Each 10 is 2 times 5. So that's how we get 2 squared times 5 squared. Here are some other ones that are a bit larger. You don't necessarily need to worry right now about how we found these. These are just to show you some examples of prime factorizations. Let's talk about how to find the prime factorization of a slightly larger number. So for example, suppose we're looking at the number 96. What is the prime factorization of 96? You might want to pause the video and work on this right now, and then I'll discuss it. So the prime factorization of 96, well, certainly it's divisible by 2, so we can express it as 2 times 48. 48 is 6 times 8. Well, from there, 6 is 2 times 3. That's the prime factorization. 8 is 2 times 2 times 2. Then group everything together. We have 1, 2, 3, 4, 5 factors of 2. So we can write that as 2 to the 5th times 3. That's the prime factorization of 96. Notice that 96 would be divisible by 2, 4, 8, and 16. Those are powers of 2. And by 6, 12, 24, and 48. Those are those 4 powers of 2 multiplied by 3. All of those would have to be factors of 96. Notice it would not be divisible by 15 or 18. It's not divisible by 15 because 15 involves a factor of 5, and there's obviously no factor of 5 in 96. 18 is a little trickier. 18 is 2 times 3 times 3. You need 2 factors of 3. 96 only has 1 factor of 3, and therefore 96 cannot possibly be divisible by 18. So here I've just shown an example of a very important idea. One way to say it is the following. The prime factorization of a number is like the DNA of the number, revealing all its essential ingredients. Any factor of Q must be composed only of prime factors found in Q. So that's a tricky idea. We're going to talk about this for a few minutes because it's a tricky idea. First thing I'll say is, remember our synonymous statements from some earlier videos. we have these four statements. R is a factor of Q, R is a divisor of Q, Q is divisible by R, Q is a multiple of R. All four of those mean the same thing. Well, we can add a fifth statement now. Every prime factor of R is included in the prime factorization of Q. That is equivalent to the other four statements. Let's talk about an example with actual numbers. Suppose we are told that 4,680 has this prime factorization. Someone just hands us the prime factorization, which is awfully nice. Given this prime factorization, we want to know which of the following numbers are or aren't factors of this number. So I'm going to say pause the video and see if we can use the prime factorization to figure out whether each number here is a factor of that number. So for 25 obviously is 5 times 5. We need two factors of 5. We have only one factor of 5, so that's not going to work. 25 does not work. 45, well, that's 5 times 9, or 5 times 3 times 3. Well, we have a factor of 5 and we have two factors of 3, so that works. 65 is 5 times 13. Well, we have a 5, we have a 13, so that works. 85 is 5 times 17. We do not have a factor of 17, so that's not going to work. 120, well, that is 40 times 3. 40 is 8 times 5, so we have a 3 and a 5 and then an 8, which is 2 times 2 times 2. Well, we have a 2 cubed, we have a 3, and we have a 5, so that we're all set. Means that this would be divisible by 120. 180, well, that is 30 times 6. 6 is 2 times 3. 30 is 6 times 5, so we get 2 times 3 times 5, so we need 2 powers of 3, 2 powers of 2, and 1 power of 5, and we have all that in the prime factorization of 4680. So in other words, 4680 would be divisible by 180. That would actually work. So we've used the prime factorization to figure out whether these other numbers could be divisors of 4680. That's just one example of how prime factorizations can be useful. In the upcoming videos, we'll be showing many different examples of how we can use prime factorizations to answer a number of different integer property questions. Finding the prime factorization of a number is definitely the single most important skill in the entire integer property section. It's critically important to practice this skill until you are extremely comfortable with it. In summary, we talked about what the prime factorization is and how to find it. And we talked about how the idea of prime factorization connects with the ideas of factors and multiples.